Eugene Demler.
Thank you, Hassan. Yes, so today we're changing the subject and we move in the direction of non-equilibrium physics, and in particular face pursuit of getting new types of matter, new states of matter using optical control. And again, I want to begin by acknowledging people who really did all the work. So in this case, Marius, who started this one, was still like this research direction, was still a PhD student at Harvard. Duilo, who came as a visiting student to my group at ITH, and we have been collaborating with them, and some Buddha, who is sharing his time between Boston and Zoom. And also in the first part of my talk, it is based on collaboration with Patrick, and that's really work in progress that I would happy to share with you. And what made today's answer, what made this kind of research direction particularly exciting was collaboration with our experimental friends, and specifically these groups by Andrea Cavalieri and Rick Hager. So in the last lecture, in the previous lecture, we already talked about this interesting frequency range of terahertz, which is difficult technically, but our friends in industry have been making, and academia have been making dramatic progress in building new devices so that we will have much more powerful sources, much better detectors. And we also mentioned that this is a very interesting frequency regime also for many-body physics, for exploring strongly correlated electron states, because many of the collective excitations or elementary excitations of in electron systems, they fall within this frequency range. And this will be cyclotron modes, which is transitions between Landau levels, which we talked about yesterday, or let's say quasi-particle gaps in superconductors, CDW materials, phonons, plasma excitations, different types of spin resonances. So a combination of these two factors, kind of rapidly developing technology, and the fact that this is a very important frequency range for many-body physics, led to the kind of very exciting developments in the type of experiments which were perhaps not so popular about a decade ago, and this is pump probe experiments on strongly correlated electron systems. And roughly the idea is that instead of the usual paradigm of linear response that we're used to from our conventional solid-state physics, here one first applies a pump at the frequency which is known to in which we know that we can very strongly excite the material, and very often this is exactly the terahertz or infrared frequencies, because this way one can excite like relevant phonon modes, other collective excitations. And then one interrogates the system, and probe can also be optical. Sometimes can be some other, say, time resolved photo emission is also an interesting direction. And this type of investigations agrees with our everyday intuition that if we want to understand the person that we don't know so well, it's very kind of informative to see how they behave in a stressful situation. Interestingly, in the last few years, actually, what our experimental friends got interested in shifted from using these pump probe experiments as a way of interrogating and getting information about equilibrium states to asking a more ambitious question: can one actually achieve new states of matter, like or maybe increasing transition temperature dramatically, or even creating states which do not have static analogs? And the kind of the overarching question behind it is a question of universality. So when we talk about classical non-equilibrium dynamics, while we know very important classes of universality from solitons to pattern formation,
When we talk about quantum matter in equilibrium, again, we have very important paradigms like broken symmetries that you heard about from Norm yesterday, like Fermi-liquid states, the topological order. So usually when we have a new equilibrium quantum many-body system, we at least know which type of phenomena we're dealing with. But I think even today, when we talk about non-equilibrium dynamics of many-body quantum systems, there is still no kind of simple understanding whether we can divide everything we see into some important classes, or maybe we're just dealing with, we should just study such problems on a case-by-case basis. So what I will try to present to you today is that based on experiments that we have seen, we see several emergent paradigms and also like in theoretical analysis. One of them is perhaps something that you have seen most often discussed in the context of light-induced states, and this is an idea that we can think about light stabilizing some metastable state. So basically, we imagine that there is some kind of free energy landscape, and then there is a true minimum of free energy, which corresponds to the equilibrium state, but then there may be a local minimum, and then by applying perturbation, we can drive the system from the global minimum to a local minimum, but the system can stay for some time. I'll try to expand this idea of metastable states. For example, I'll show you that there is a path in which we can get this long-lived sort of like quasi-static picture of non-equilibrium states, which doesn't really have a simple interpretation in a sense of free energy, and it has to do with dynamical properties. I'll give an example of so-called quasi-particle bottleneck. But then I will also give you two other examples which are very orthogonal to the idea of this kind of metastable states, and these will be material properties which rely dramatically on the fact that we're dealing with non-equilibrium systems. And in one case, you will see that some of the surprising optical properties of these transient states can be understood once we take the perspective of like a matter of materials in which system parameters are not constant in time, but are oscillating. And the other perspective is that the strong driving of the systems can result in very non-trivial nonlinear dynamics, and so signatures of nonlinear dynamics, one should not immediately kind of, they may at first glance look like something we're used to in equilibrium systems, but they may present a completely different class of phenomena. Okay, so this is the outline of my talk. I'll start with one of the most recent, by discussing one of the most recent experiments in this field by Andrea Cavaleri's group, and this is the so-called light-induced Meissner effect. At least this is how they call the experiments. And I'll try to give you a different interpretation of these experiments. Then I'll take a step back and tell you about early experiments, which were also interpreted as light-induced superconductivity in this class of materials. And I'll show you that we can interpret them from the perspective of Flaquier matter. But in order to do so, I'll need to introduce some kind of basic idea of this kind of optical properties of materials with excited collective excitations. And then I'll show you that the same argument works not just for superconductors, but also in tantalum nickel selenide. Experiments in Recovery's group show very similar behavior. And then finally, we'll talk about surprisingly long-lived superconductivity, photo-induced superconductivity in this buckyball superconductor, and the big difference between like the first examples, like when we talk about, let's say, light-induced superconductivity in YBCO, we talk about picoseconds. Most of the kind of light-induced phenomena, they have a characteristic lifetime of picosecond. It's kind of roughly, can say, think about it as lifetime of excited phonon, say, or any type of excitation. But in the case of this K3C60, they managed to achieve superconductivity on the scale of nanoseconds, and that will clearly require a different type of an explanation. Okay, so let's begin by talking about experiments done in Hamburg, which they interpreted as dynamical Meissner effect. Again, don't hesitate to interrupt me with questions. So let me remind you what is Meissner effect. So if we have magnetic field which penetrates through a material, and okay, there may be diamagnetic response, but typically this diamagnetic response is 10 to minus 6, 10 to minus 5, right? It's very small. But then when we, if this material goes superconducting, magnetic field is fully expelled, right? So we talk about perfect diamagnetism. But there is another side to this, as we recall that, of course, magnetic field lines cannot be just terminated. So if magnetic field is screened out from inside the material, this means that we get an increase in the density of magnetic field right outside of the sample. Okay, and now we, again, I will not go through all the details of high-temperature superconductors, but for non-experts, let me just point out that there is a very surprising regime, which is called the pseudo-gap regime. So it's a state of the system which is above the equilibrium TC, like below TC we have a regular Meissner effect, but above TC we have very strange properties, and people are still debating, does it arise from kind of some other type of order, or is it because we have superconducting fluctuations? So the debate about the nature of this phase continues for a while. And now the Hamburg group has added an extra puzzle. An extra puzzle. They demonstrated that they can induce very non-trivial photomagnetic effect, which they interpreted as light-induced Meissner effect. So let me explain exactly what they did. So they take YBCO, and so it's a layered superconductor. So these green lines you see, these are layers. And well, we also said that all of the light-induced phases, at least in YBCO, live picoseconds. So if they want to see like change in magnetic response, they cannot do it in a traditional way, sort of like, I don't know, any kind of squid magnetometry is too slow. So they came up with a very fast way of measuring magnetic responses, which is based on the following. So they actually take a material, gallium phosphide, which has a very strong Kerr effect, which basically means that if one sends light with some polarization, this polarization will rotate by the amount which is proportional to magnetic field inside this gallium phosphide. And that it's an optical probe, so it can be done very fast on picosecond timescales. And okay, well, they want to excite the system. Okay, we'll talk in more detail later what exactly, how exactly they're driving, but it's like somewhere like light, basically, like terahertz, like mid-IR frequency range. But they also want to make sure that, you know, like the detector, this gallium phosphide material, is not affected by the pump. So they also put an extra layer, which is kind of like protects the detector gallium phosphide from incident light. So, but it also protects then the part of the superconductor below it from incident light. So effectively, what we see is that there is a part of this material which is illuminated by light, and then there is a part under the detector which is right outside of where material is photoexcited, and this is where they measure magnetic field. And what they saw is that when they send a pulse, a strong pulse of light, they see a dramatic change in magnetic field. So in fact, just to give you an idea, if we think about static diamagnetic effect in YBCO above TC, we talk about 10 to minus 5. That's, for example, why actually people have always made, at least not always, but there has been kind of an argument against existence of superconducting fluctuations above TC, or like its prominent fluctuations above TC, just by saying, oh, this diamagnetic effect is small. Okay, but so that's a static value. But then what they see, like after, like in the presence of the strong light pulse, they see a response of the order of 10 to minus 3. So there is 100 times stronger response. However, what they see is really not diamagnetic response, but they see paramagnetic effect. It's kind of the opposite of Meissner effect. The explanation is, well, look, so there is this part of material, which is, they turn into a superconducting state by shining light. And then this part then is like an outside of the superconducting. If we make the inside of the material like perfectly diamagnetic, or it is strongly diamagnetic by photo-inducing superconductivity, then magnetic field lines are expelled. And so if we're measuring outside, we should see paramagnetic effect. And the effect is quite robust. Okay, questions? Yeah.
Doesn't it like heat the sample and probably raise the temperature?
Sorry, how big is what?
The heat the sample because of application of the pump.
It probably does, but that would not make it superconducting, right? So that's in a sense a surprise. Like naively, if you send a strong light pulse on the material, indeed you just make it hotter, and that would suppress all types of instabilities. So the question is, how can you induce something with light? Okay, and just to give you some ideas, so yeah, we talked like this response is a kind of nonlinear function of the intensity of the pump pulse, and it disappears only at very high temperature, basically room temperature, right? So this basically the kind of statement of this paper is that with light they can induce superconductivity at room temperature. Okay, so there are two kind of obvious scenarios which we can consider, and one is which an experimental group suggested, well, that we have light which really induces superconductivity. The second one is that, well, maybe we had some superconducting correlations, and by driving this, by applying the strong excitation, we actually revealed this correlation. We somehow made them much more dramatic. So let's try to understand whether we can make a kind of more accurate model based on one of these scenarios. So one of the kind of pieces of physics that I want to introduce to you related to superconductivity is Josephson effect in layered superconductors. And basically, it's an idea that, well, superconductivity is like a condensate of Cooper pairs, and then these Cooper pairs can coherently tunnel between the layers. And if we introduce phase of Cooper pairs within each layer, then the minimum of the energy is achieved when this phases are equal, or like difference is multiple of 2 pi, and coupling is described by this cosine of the phase difference, which also means that current between the layers is proportional to sine of the phase difference. And what comes together with this idea of kind of Josephson coupling between the layers is that, okay, well, due to thermal fluctuations as a result of dynamics, one can get what is known as Josephson vortices. So we know that the energy is minimized when it's a multiple of 2 pi. So there may be like a part of the system where the phase difference, let's say it's 0, and then it changes by 2 pi, right? And it faints, and kind of it's a finite energy excitation kind of domain world. We can then just look at behavior of the phase and expression for the current. We see that it corresponds to the current, which makes this kind of vortex-like pattern, right? You can just see, because interly current first goes up when the phase difference between 0 and pi, then it goes down when it's from pi to 2 pi, and of course charge has to be conserved, so we make a loop. And one can also compute what the typical length scale of this Josephson vortex is, and it's inversely proportional to the strength of Josephson coupling between the layers. Okay, so this is kind of static property. There is a closely related dynamical property, and this is the idea of Josephson plasmons. So we have 2 layers, and now let's write equations of motion for Cooper pairs, right? And let's just introduce a phase difference between the layers, like charge imbalance, difference of electrochemical potential. And what one can do is like take standard equations of motion for the phase, like for example, the time derivative of the phase is difference of electrochemical potential, or like current expressed in terms of the phase difference, not go through all the details, but what one finds is that the relative phase is dynamics of the relative phase, if it's uniform in space, is described by this familiar equation of just a physical pendulum, right? And this, of course, gives us a characteristic frequency, and we see that the frequency goes as square root of Josephson coupling between the layers. And when we look at YBCO, it's actually has a special feature. It's what is called bilayer material, which means that inside each unit cell, there are two layers with a much smaller distance between the two layers inside a single bilayer than distance between different bilayers. So if one looks at the ratios of Josephson plasmas, right, which arise from these couplings, one finds a difference of frequencies of a factor of 10, which means that the difference of Josephson couplings is a factor of 100, right? So we get dramatically stronger coupling, Cooper pair tunneling within each bilayer than between different bilayers. Okay, well, with this argument, it is then natural to make the following model. Well, when we suppress superconductivity, this means we suppress coherence between the layers. But we have such separation of coupling strength, then we can imagine that what's happening is that we suppress coherence between different bilayers. But within single bilayer, there is still a kind of a phase locking, right? Because the relative phase between the two layers still wants to be 0 or a multiple of 2 pi. So like the phase inside each layer, right, is fluctuating in space. But then the phase in the second layer sort of roughly follows the kind of spatial configuration of the first phase. So let's then study what would be the properties of this regime in which we still have some phase locking within bilayer, but essentially decoupled bilayers. Okay, so first of all, in this regime, we do not expect like real Meissner effect. Let me remind you that if we think about real Meissner effect, we apply external magnetic field, and then we need screening currents which go all the way through on the surface of the superconductor, and they screen out this external magnetic field. But now, if we apply external field, we can have some screening currents within individual bilayers, but we cannot have a static screening currents like connecting the two bilayers. Therefore, there is no Meissner effect. We can also promote this equation to dynamics. So in a true superconductor, actually, one can sort of do analysis similar to what we discussed before, and we'll talk about it later as well, that one can write equations of motion, let's say for magnetic field, which combines equations of motion of matter, like how currents respond to electric field in superconductors and Maxwell's equation. And you can, let me just sort of show you that it reduces to what you expect. Imagine that we're looking at the static case, right? So time derivative is 0. So for this bulk superconductor, we immediately see equation which describes exponential decay of the magnetic field. So that's the familiar Meissner effect. On the other hand, when we look into kind of dynamics, with like if this London penetration depth is infinity, which means no superconductivity, well, we just get some renormalized light propagation. But as soon as this London penetration depth is finite, we see that we actually do not, we introduce a finite gap to electromagnetic excitation. And this is a celebrated Higgs kind of mechanism of giving mass to electromagnetic fields inside the superconductor. Okay, so what we can do, we can generalize. Okay, well, the first question we can ask, so in this model, like say if it's static, just static screening effect. So we do get some partial screening currents within each bilayer. So can we compute what this will be? For this, we have to generalize these equations. And we do it like I show it here, and I will not go through the details, but you can roughly see the structure. So within, like now we have to write it separately for kind of the part of the system within each bilayer. And it looks very similar to what we wrote for a bulk superconductor. You see that there is a term which is analogous, like it doesn't have any derivative, so it's analogous to the standard penetration depth that describes screening current, but it's only within bilayer. And between bilayers, then actually we see something that corresponds to kind of a normal state. We do not have this Higgs phenomenon. But the two fields are coupled to each other just by Maxwell's equation, right? So we cannot write. Basically, you can think about this as capacitive and inductive coupling of currents and electromagnetic fields between the two layers. So what we can do now is set the time derivative to 0 and compute what would be the diamagnetic response in the static case. Well, if we take typical numbers for the superfluid density, like in one layer, we actually arrive at exactly this number of 10 to minus 5. So our model of kind of residual superconductivity within bilayer does not contradict data that we have for static diamagnetism. Okay, but now we want to study dynamics. And to make life simple, let me first focus on what's happening in a single bilayer. And let me promote this kind of model, which previously what I wrote to you was effectively kind of linearization around equilibrium. Now let us promote it to the full dynamics. And you can also see that equation that I write is kind of generalization of this mathematical pendulum that we discussed before. So there's a time derivative. There is also like that in energy, this would be cosine. If we look at equations of motion, there is a sine. But now there is also spatial gradient. And I also consider the case which is relevant for our discussion is that there is also a small static magnetic field, because after all, we're looking at the analog of Meissner effect, so we should apply static magnetic field. And then there is a new term, and this comes from electric field. And I forgot to mention this light-induced Meissner effect is only observed when light is polarized in such a way that electric field is perpendicular to the layers. But you really have to drive currents between the two superconducting layers. And so when there is an electric field applied, we know that we just have to add a driving to the kind of the sign-Gordon model. Again, celebrated Josephson equation that time derivative of the phase is equal to basically voltage difference across the superconducting junction. Okay, so and we need to supplement this equation by boundary conditions, and like the simplest one we can take is that there should be no currents at the edge like of the material, which means that the spatial gradient like of the phase at the boundary should be equal to 0. Okay, so magnetic field is very weak. One can think about it's like much smaller than HC1, like in the equilibrium state, or you can also ask, or if we started putting, when we talked about Josephson vortices, like so we would, like if we start really densely packing Josephson vortices compared to that, and to that field, we're looking at fields which is like 10 to minus 3. Well, they drive actually at a frequency which is close to the resonance frequency of this Josephson plasma. So from that perspective, while the system should be quite responsive. But what is most dramatic is that they drive really strongly. Because if we think about the typical phase winding across the system, we can estimate it by saying, okay, like if there is electric field of the pulse, voltage difference is this electric field times the distance between the layers. And if we integrate, or let's say half a period when voltage doesn't change sign, we see that the phase winds by a lot, right? It's, in fact, for kind of the strongest drives that they apply, they were literally burning holes in their samples. So they had to reduce kind of light intensity that they applied. So, but you can at least see that kind of they're taking this Saint-Gordon model way out of equilibrium by sort of applying, like inducing such a huge phase difference in between the two layers. Okay, well, now what we want to understand is just look at dynamics of this specific model, right? We assume that there is still residual superconductivity within one bilayer. Bilayers are decoupled, so let's write equation, kind of study dynamics in this case. And I changed my variables slightly, so I sort of go into the frame, which you see that this, instead of simple phi, it actually is shifted. So the way you can think about this phase shift, it's roughly an argument that now when Cooper pair tunnels, there will be a Lorentz force from the static magnetic field, which will give Cooper pairs finite momentum, right, when they arrive in the next layer. And this can be described exactly by the fact that there is some phase winding in X. And so we shift the phase in this manner. So now equations of motion look like familiar kind of driven Sine-Gordon models, but we have to modify boundary conditions that now effect of external static magnetic field is to have finite gradients at the boundaries. And these gradients, like they're controlled by the magnitude of magnetic field. And basically we can make it kind of in units of the corresponding Josephson length, we can make it dimensionless, and it's very tiny. So that's basically of the order of 10 to minus 3. So in equilibrium, we start in a configuration in which like this phi tilde is actually uniform in space, which but actually now our current it's like gradient of phi tilde minus q. So this means that we have counterflow currents going this way, and then we also, but then the gradients of phi tilde have to be finite at the edge in order to satisfy boundary conditions, and this corresponds to this kind of small edge screening currents that we discussed. Right, so therefore, this is this kind of tiny Meissner effect, static Meissner effect that we get within individual bilayers. But now what we do, we start applying this strong but uniform electric field. And we see something remarkable, that at time equal 0, we only had this like a tiny phase winding at the edge. But when we apply uniform driving, right, what it does, it suddenly like dramatically amplifies this small gradient at the edge. It's like, if you think about it, what was happening at the edge, well, like the system only allowed like a small fraction of a vortex to penetrate, like 10 to minus 3 of a vortex. And uniform drive, naively, it doesn't do anything, right? Because it's uniform, so it doesn't favor by itself, like a uniform drive between the layers would not favor currents flowing to the left or the right, like a soliton, like winding by 2 pi or minus 2 pi. However, the fact that we had a seed of the soliton at the edge together with the uniform drive turns out to actually dramatically amplify the soliton. So you can think about it some kind of a soliton ratchet, like it really sort of takes this tiny tail of a soliton, tries to drag an entire soliton. So what you see here is that this kind of this quantity, it's an integral of the phase gradient over the entire system. And like, as I said, we start before the driving pulse arrives, this being very, very small. And then as the driving pulse arrives, it's really kind of amplified dramatically. So it's some kind of instability in the Sine-Gordon model, which interestingly, like we really first saw this numerically, and it's not something that we have not seen discussed in the literature before. So, okay, and then what we can check is like, so what is this type of dynamics, like some special case, we were just lucky to choose magnetic field, and the answer is no. So basically you can vary the kind of a static magnetic field which you apply, and you find that the amplified value of the current at the edge scales linearly with respect to the static magnetic field. So that's exactly what was in an experiment. That's why they interpreted as a Meissner effect. Response was proportional to magnetic field. We also see nonlinear response, nonlinear dependence on the drive. So there is one actual subtlety here, which I will not comment. Like, it turns out that dynamics does depend on dissipation, but again, I'll be happy to talk offline. So we do need some dissipation, but it's not surprising that there will be dissipation. After all, we talk about fairly high temperatures, and it's a D-wave superconductor to begin with. So there are many quasi-particles available. So, okay, so how do we think about it? Well, interestingly, the kind of first somewhat related work that we found was done in the context of cosmology. So this was the work of Stravinsky and company, and they asked the following question. Like, they were really interested in some kind of inflation scenarios, but they investigated like Sine-Gordon mode, and they said, let's take Sine-Gordon mode, which is not an equilibrium configuration when the phase is at 0. Let's displace it uniformly, right? And then let it go. Naively, you would say, oh, we start with a uniform configuration, so we'll just get oscillations in the system, but this oscillation will stay uniform. But then they considered deviations, basically fluctuations on top of this uniform solution, and they found that they're unstable. And indeed, from the point of view of the small fluctuation, kind of uniform oscillation, they provide a parametric drive. It's kind of something that you hopefully remember from your childhood experience. Like as a child, you stand on a swing, and then as soon as you have kind of like a little bit of initial push, then just simply standing up and down, like with the correct period, like in resonance with the oscillations, you can actually amplify the amplitude of oscillations. And you're not like you're on a swing, you're not physically pushing the swing, you're only changing the moment of inertia. But this kind of periodic changes of parameters of the oscillator, like in this case, like it's an approximation of a harmonic oscillator, is enough to amplify oscillations. And that's exactly what's happening here. It's a parametric resonance from the point of view of small fluctuations, and so small fluctuations get amplified. And then this idea was taken by, like much later, taken up by Florian Marquardt and Anatoly Polkovnikov and Clemens Neunhan, where they said, well, this Sine-Gordon mode is what one can prepare with ultra-cold atoms, and there one can also very naturally realize the situation in which the kind of like Sine-Gordon system is taken out of equilibrium and just applies a bias voltage between the two layers, and then looks at oscillations. And they saw essentially, like first numerically, that the same effect, that like any kind of fluctuation put in quantum zero, 0 point, like quantum fluctuations get amplified, and they, if oscillation is strong enough, they can develop into breathers and solitons. So effectively, what is happening in the type of physics that I'm describing you is that, like while in the papers by Starobinsky et al., Marquardt et al., they were amplifying just initial noise, like the thermal noise or quantum noise. Whereas in this case, we're amplifying these kind of tiny fractions of the solitons, which were at the edge, right, in the static configuration. But once we apply, and also like the drive of the kind of center of mass of kind of the uniform configuration in our case is not kind of just because we shifted the system out of equilibrium uniformly and let it go. No, it's actually induced by external drive, but the picture is the same. We're just getting parametric resonance, which amplifies the small solitons and makes them explode. Okay, so like when we realize that there is this interesting instability in the Sine-Gordon model, there is still some work that we have to do to connect to experiments, because, okay, so we get some extra currents at the edges of the system. We, in fact, one also needs to take into account that in real materials, like we do not really have like this infinite perfect crystals, but really we should think about finite segments of the length of maybe tens of microns. So like at the edges, we get these tiny currents, but then how does it get converted into magnetic field? That's measured in the detector. And first, we have to understand how these edge currents get converted to magnetic field, which penetrates like still inside this. So I guess like just to give you maybe what I'm trying to represent here. So this kind of in yellow, you can see the part of the material, right, which is illuminated by light, right? And you see this kind of layers, which are, but only I emphasize more the bilayer character. So like within each, and then what is above, so that's really part of the sample, which is under the mask, right? That's where the actual measurement is done. And so first, we have to solve how the edge currents generate field still inside the illuminated region, but going inside into the interior of the segment. And that actually turns out to be quite interesting. So say regions between bilayers turn out to be important, and it's really, they provide kind of a waveguide. So once we generate magnetic field, it goes into the bulk. But Also, another interesting subtlety is that, like after all, we know that flux is conserved, so we cannot just generate positive magnetic field and no negative magnetic field. So what this shows is that once we generate positive magnetic field inside, we actually generate negative magnetic field. But I point out that there is actual difference in what I'm showing, like what our calculations suggest that even in the light in the part of the superconductor that was illuminated by light, we're actually getting a paramagnetic effect. We're sucking in vortices, right? When vortices come in, you make the system less diamagnetic. So, and then this kind of paramagnetic effect, it's generated in the illuminated region, and then it propagates into the part under the mask roughly with the speed of light in the system, which again you can get by solving Maxwell's equation. And this is where it is now being measured, right? So this part is like basically this here vertical axis is like this axis in the experimental geometry. And if we look at the magnitude of the effect that we can get, we get also this factor of about 100 that they have seen in experiments. So, okay, so then what do we learn? Well, it looks like we can explain this dynamical Meissner effect without really saying that there is a mysterious phase which was created by light. Well, does it mean it a boring story? No, we don't think so, because we rely for the story on the existence of sufficiently strong superconducting correlations all the way up to room temperature. So it means that actually in equilibrium already we had strong correlations. However, traditional probes like diamagnetic response, like the usual optical conductivity, this perturbative type of interrogation of the many-body state could not reveal it. But once we took the system very far out of equilibrium, which they did with the strong pulses, then they managed to resolve that, to demonstrate like this dynamics, which is peculiar to superconducting systems. And our prediction also comes with a false, our model and result comes with a falsifiable prediction, right? Because as we said, experimentalists suggested that the reason they see paramagnetic effect is because in the part which is illuminated by light, there is diamagnetic response, whereas our model indicates that if they measure kind of magnetic effect in the part which is illuminated by light, then they should already see paramagnetic effect there. And so it's not really because the they created a kind of diamagnetic region in between, but because instability naturally generates a paramagnetic type of response. And so that now, like within the paradigms that we consider, this just shows you that there is a very interesting dynamics. However, in this case, it is not, it's enough to just write semi-classical equations of motion, and it is nothing which would be like really particularly quantum about it, except of course it relies on superconductivity, which is kind of a macroscopic quantum phenomenon. Any questions about this part? Okay, but as I told you in the beginning, this was not kind of the first experiment indicating that one can use light to create superconductivity in YBCO. Actually, the same group has done other experiments, and in the story, we again remind you that we're dealing with a material that's bilayer material. We have two types of Josephson plasmons at high and small frequency. And so one can also kind of take equation that I showed to you before and work a bit more with this and get full dispersion of these kind of polaritons, which are hybrids of kind of electromagnetic radiation and now currents flowing in the system. And again, we get, so at zero momentum, these two plasmons that we discussed before, like 1.5 terahertz and at 15 terahertz, that's the dispersion. And the fact that there is a gap in the spectrum immediately shows up in reflectivity, right? Basically, this gap, you can also think of, it's the same Meissner effect, right? Okay, magnetic field cannot penetrate, which means that at small frequency, light cannot penetrate into the superconductor, and that's why there's perfect reflectivity. Whatever we send into the superconductor needs to be reflected. But once frequency goes above this lower Josephson plasmon frequency, there is a drop in reflectivity, which is called the Josephson plasmon age. So that's kind of theoretical calculation of reflectivity, and this is roughly what they measure in the superconducting state. You see this lower Plasma H, and then there is an upper Plasma H when one crosses in frequency the threshold for the second plasma. Okay, but kind of our Hamburg friends, like some time ago, did another experiment. They really were measuring these Josephson plasmons in like not that, just many groups were measuring Josephson plasmons before, and they were always considered like the golden standard of superconductivity. So you really have to be below TC, let's say in equilibrium, the pseudo gap phase, one does not see this Plasma H. And what they decided to do was, again, well, what happens if they go into like what happens to the system if they now excite it very strongly with this kind of infrared, like terahertz light? How does optical response change? Okay, so below TC, something interesting happens. So this is color coding of reflectivity. And you see, like this is earlier times is before the driving pulse arrives. And you see this is this lower Plasma H that we discussed before. But then the driving pulse arrives, and there is a new feature which appears at really high frequency. And they talked about it as light-induced Josephson Plasma H. And you see how kind of dramatic it is. It is at much higher frequency. It's as if they, by shining light, they made a much stronger superconductor. And things become even more dramatic above TC in the pseudo gap phase. So in this case, in equilibrium, you don't even see much of a Plasma H, right? So this is color coding, or this is the cut like in equilibrium reflectivity. We don't see this Plasma H. But then when the driving pulse arises, so what is plotted here, there is a change in reflectivity. There is something which appears, like which is reminiscent of this Plasma H in equilibrium. But notice something interesting. The frequency at which it appears, at this edge appears, is really high. It's actually even higher than the Plasma H at very low temperature in the same material. So if this was light-induced superconductivity, it's a remarkably strong superconductivity with Josephson coupling stronger than the equilibrium Josephson coupling at T equals 0. And that was kind of like the first series of experiments where people started talking about light-induced superconductivity in YBCO. And let me point out that these kind of dramatic changes in reflectivity is not something which is special just to superconductors. Say one can take this TNS material, and you may have heard it discussed in the context of excitonic condensates. So for what I'm discussing, these excitonic condensates it's not particularly important feature, but there is actually a dramatic change in response. I will just focus on low temperature part. So this experiments by Recovered's group, and what they did was to start with kind of measure optical reflectivity at small frequencies, again, terahertz frequencies, and then excite it. But in their case, they were actually exciting at much higher frequency, right? So basically, we're talking about frequencies like a couple of orders of magnitude higher than the frequency that they're measuring. So it's, again, very different from what we discussed say for light-induced superconductivity. So there, while they were exciting at frequencies which were higher, but not too much higher than at which they were measuring. Whereas in this case, they excite at frequency like which is 2 orders of magnitude higher, but they see also dramatic renormalization of reflectivity. They see some extra peaks, and in fact, this enhancement can be as large as 20%, and it's peaked somewhere around like 5 terahertz. So they seem like completely different phenomena, but I will try to convince you that they actually have a similar explanation. So we'll try to find a unifying model. Okay, so let me first present to you the kind of qualitative physical picture. And I will do it by giving you kind of like a condensed matter version of optics. So the version of optics from the point of view of condensed matter person, which is obviously very simplified. So we have light, which is incident on a solid, let's say on an interface, in our case, interface of a solid. And then we want to understand how light gets transmitted or reflected. For this, we need to understand how light gets propagates, right? So, okay, frequency is conserved. We need to find a new wave vector, which we find by, this familiar equation that we discussed before, right? Where we have index of refraction, which can depend on frequency. And once we know the wave vector, we can write transmitted wave with a new wave vector. We can write reflected wave, and we can write boundary condition, which is just matching electric and magnetic field at the interface. And from this, we immediately derive the celebrated Fresnel reflection formula, which gives us reflection coefficient in terms of index of refraction. Now, let me, at this point, make a phenomenological assumption that while, after all, we applied a very strong drive, and actually we apply with it, like I try to advocate that when you apply your drive at sort of terahertz frequencies, there are many excitations which have very similar frequency. In fact, it turns out in the case of YBCO, the drive that's applied is resonant with one of the phonons, and we'll discuss this later. But for now, there is some excitation which we created. And then index of refraction is no longer constant, but it's actually oscillating in time. Now, what we can do, we can, so our system becomes kind of like hair matter, right? Index of refractions is a periodic function of time. And what we do is we now have to modify how we solve the problem of light propagation inside this Flaquet medium, right? Because previously in a static system, well, if we have incident light at one frequency, it will propagate at the same frequency. But if we have time varying index of refractions, then we'll get frequency mixing. And in particular, there will be a very important effect of parametric resonance, which we discussed before, right? And you can think about it as oscillations of the index of refraction generating pairs of excitations, right? And they have to be generated in such a way that the sum of their frequencies adds up to the drive frequency. And like in quantum optics, this is usually called signal and idler. And so when we write the equations on just the propagation, we have to modify this equation to couple the different frequency components. And notice that this frequency, like the signal comes in with the usual minus sign in the exponent, but the idler component with the plus sign. And that is an indication of the fact that we're actually generating excitation. It's a parametric resonance. And we have to sort of now solve this coupled equation for the signal and idler component. So instead of like a single equation for just one component, one frequency component, it becomes a sort of a two-component equation. And we can get mixing. And when do we expect the strongest mixing? Well, when then there is actually strong coupling between the signal and idler, and each of them will have, like once we know frequency, we can compute the wave vector. And if these wave vectors are close to each other, then hybridization and mixing is most efficient. That's what in optics is called phase matching. And of course, will be kind of good phase matching if both signal and idler have the same frequency, therefore the same wave vector, and that's half of the drive frequency. So we expect this parametric resonance to be most dramatic at half of the drive frequency. And then all we have to do is just, okay, take a solution of the Fresnel problem and generalize it from what we had before for one frequency component to two frequency components, and write what would be the change in reflectivity. And naively, you would say, oh, that actually what we're going to get is something which is very non-universal. Surprisingly, so what, as Mario showed, you get a very kind of universal type of response. You can express change of reflectivity just in terms of equilibrium properties like reflection coefficient, index of refraction, and frequency at which we have parametric resonance with some coefficients. But I'll just focus on the most important feature. So naively, you would imagine that, oh, if we have parametric resonance, like our drive generates additional excitation, like so in reflectivity, we may expect extra peaks. Well, life turns out to be more complicated. There is a competition between this parametric driving and dissipation in the system. So it's somewhat similar to the so-called Fano problem, right? If you remember in quantum mechanics, when you have, let's say, two harmonic oscillators, and one of them is overdamped, the other is very weakly damped, and we're looking at absorption of the systems of two harmonic oscillators. And the way the system absorbs can have very peculiar features, in which we have either peaks or dips, and this basically dip can be thought of as destructive interference. So absorption by the kind of two harmonic oscillators, they can destructively interfere. And that's kind of what we have here, because well, like instead of two oscillators, now we have two channels of absorption, like signal and either. And the way they interact with incident light kind of results like we have to do it in a coherent manner, and there may be constructive or destructive interference. And this is determined by the competition between dissipation and the drive. And so if dissipation dominates, instead of the peaks, we can get actually dips, or we can get shoulder type of changes in reflectivity. So let me also point out that, okay, when we did this, we learned that it's actually not so far from what has been an active field in photonics, and it has the name of photonic time crystals. So people who come more from kind of many-body condensed matter background, then like we think of time crystals as something else, some kind of spontaneous breaking of time translational symmetry. Whereas for photonics, this time crystals really means it's just like properties of photonic properties of systems in which index of refraction changes in time on time scale, which are comparable or even shorter than the period of this electromagnetic radiation. And so let's say they were looking, in particular, they were already discussing question of what if index of refraction suddenly changes in time rather than in space. And they were also talking about this, or just like, you know, the usual refraction changes different momentum. When we have a change in time, it starts, we start mixing different frequency components. That's exactly like a picture that we're used to in condensed matter. But what is interesting is like this photonics kind of photonic time crystal discussion was all done in the context of optical frequency, and it's really makes it very hard to do experiments because well, like timescales are very short, and therefore it is extremely challenging to change index of refraction on timescales, which is set by optical frequency. So by contrast, when we think about terahertz frequencies, well, periods are much longer because frequencies are smaller. And secondly, we have this natural helpers of in the form of collective excitations, right, which have roughly the same frequency, and therefore they naturally provide modulation of the index of refraction at the frequencies comparable to terahertz light, which we can use for the probe. Anyway, so I guess what you can say that this is my advertising that actually kind of the photonics community may find it fruitful to apply, let's say, some of the ideas that they had to the terahertz regime. I think this discussion has already started. Okay, but now let's take this general formalism, which we considered, and try to apply it to specific cases that we discussed, specifically YBCO. Okay, so as I advocated before, like when they apply drive, they usually they have to excite resonantly one of the photons. So these are very specific photons which have to do with the motion of oxygen, like toward this copper oxide plane. There are two of them, and roughly the difference, so one is around 20 terahertz, the other is close to like 16 terahertz, or I think it's actually this number is not correct, but it's like roughly around like 4 terahertz frequency difference. And what there was some kind of ambiguity what exactly was happening, but by now it looks like experiments converged on the fact that they see these photo-induced edges only when they excite both phonons, like at 20 and 17, like 16 terahertz. And so what this means is that if you have excite both of these phonons and they are active, then we can consider perturbation that corresponds to absorbing one and emitting the other, and that will be now of the Raman type, right? It will no longer have electric dipolar moment, so it has the same symmetry of index of refraction, so it can modify index of refraction, and moreover, it will have it to take place at the frequency, which is the frequency difference, so it's roughly kind of this kind of 4 terahertz. And then what we can do, we can compute what is the change in reflectivity just by taking kind of this equilibrium reflectivity pattern that we know for Josephson plasmons, but taking different models. Like in the case of superconductor, like below TC, We take the mode of under-damped Josephson junction, right? It's a good superconductor, not so many quasi-particles. And then we get the structure, which which is kind of exactly the resonant frequency of half of the driving frequency. And if we take situation above TC, then actually what we see is exactly what we discussed before, the case of a kind of strong dissipation. We get the Schroeder type features for changes in the reflectivity, which match very nicely what was seen in experiments. Okay, so this was for a superconductor. What about TNS? As we said, there was a strong enhancement of reflectivity, even though like now driving is done at much higher frequency. So at these frequencies, we're no longer exciting electrons, we're exciting, so we're no longer exciting phonons, but we're exciting electrons. This is some kind of interband transition. So this material is an insulator. And, but then the question is, well, if we see an increase in reflectivity, is there anything that could account for like this specific change in reflectivity? So Marios took his general formula that he derived and tried to kind of fit it using equilibrium reflectivity and assuming oscillations. And he found that he can get a reasonably good match to experimental data by assuming that there were kind of oscillations at the frequency of 9.5 terahertz, so much smaller frequency than the external drive. Is this frequency in any way special? Well, the only special thing that we found is that there is an IR active phonon, but it's at half of this frequency. And so how do we reconcile that the fact that we're driving at much higher frequency and we're exciting this phonon? And also, where does this factor of 2 come from? Well, to make a long story short, so what's happening is that when a pulse arrives, right, there is interband transition, right? And so like direct coupling between light and this IR active phonons is very strong, is very weak just because of frequency mismatch. However, what the pulse does, it changes the occupation numbers of electrons. And now we can kind of do basically Schiffer-Wolf transformation and ask, so what does the change in the electron occupation do to these phonons? And you can very easily show that like the interband transition itself couples linearly to the phonon, because, well, interband transition is IR active, phonon is IR active. But now kind of the occupation by symmetry can only couple to square of the phonon frequency. So from that perspective, when we change the electronic occupation number, from the point of view of phonon, it's as if the spring constant has suddenly been changed, right? And of course, when you, if you take a kind of harmonic oscillating equilibrium, you change the spring constant, you know that quantum mechanically you excite this breathing motion, right? So this will be really oscillation of Q square rather than Q. And also it was kind of remarkable that after we sort of, like Marios found phenomenologically that must be what's happening, we asked our colleagues as Angel Rubio's group, so is there indeed like strong coupling between electrons which have been photoexcited and that specific phonon? And indeed, like it just so happened that exactly like in this part of the Brillouin zone, and you can see like once you choose a frequency with which you photoexcite, you will create sort of electron hole excitations in different parts of the Brillouin zone. So here, either it was kind of a luck or it was kind of experience and insight by our colleagues, but they excited exactly with the right frequency to generate electrons which couple strongly to these phonons. And so from that perspective, then it's clear why the type of modulation that we observe is twice the frequency of the phonon. Effectively, what modulates the index of refraction, these are now oscillations of Q squared. So what has been done in this experiment, therefore, is exciting not kind of the phonon in the linear way, but it was more like the exciting of the phonon squeezing, right? So that the Q squared is vibrating in time, and that gives us the required factor of 2 to explain why oscillations were at 9.5 terahertz. So how am I doing in time?
Oh, fine.
But only a few. Well, just to get, well, because Another option is I can maybe move this part to my third lecture. Yeah. Yes, yes. Usually all the lifetimes of phones of the order of picoseconds. Well, but I think, okay, so I guess I maybe lecture turned out to be longer than I expected. I think it's a kind of natural place to break because like now that if you start discussing light-induced superconductivity K3C60, it's a kind of a longer story, so I don't want to break it kind of halfway. So let me stop here and I'll take all the questions that you guys have.
Thank you. How it is related to the excitation of the band.
Oh, so see, if you start with this microscopic Hamiltonian, you do Schiffer-Wolff transformation, and now you can you can derive a coupling between this is the C1 dagger C1, let's say it's occupation in, let's say, band 1, right? But now it's coupled to Q squared, right? And this is occupation in band 2, whereas band 1 and band 2 is basically this conduction and valence band. So what the pulse does, right? It really transfers electrons, let's say, from band 2 to band 1. And so this changes these numbers, this occupation numbers of electrons, which sort of provides coupling to Q squared.
Thank you very much, Eugene. We'll take a very short break, like 2 minutes, but if you have, which means, yeah.